From the beautiful studios of Way Happy, this is Mr. Meyer here in Livermore, and we are talking 2.5 real zeros. Now, what do you have to know? There's this thing called the fundamental theorem of algebra that says if you have a function of degree n, so x to the third or x to the second or whatever, right, that you will have that many complex zeros. So x to the third will have 3 zeros. X to the second will have 2 zeros. X to the seventh will have 7 zeros. It says some of those zeros may be repeated, but that's how many you will have. Then there's the linear factorization theorem also, and that just tells you that you can factor it so that you can see those zeros. Now, the good news is that those two theorems tell you things like there are zeros, but they don't tell you how to find those zeros, and that's kind of a bummer. One more thing you might want to know is that if you know that x is a solution, so x equals 5 is a solution, then it's also a root of the equation. That means that the equation would equal 0 at that given time. It's x minus whatever, so x minus 5 would be a factor, and that's all that I'm kind of saying here in this middle part. So now finally, let's get down to this part down here where I have an example. And the first thing I want to show you is write the polynomial in standard form, find the zeros, and find the x-intercepts. So here you go. Look at this thing. It's all factored out for us. So writing it in standard form means I got to FOIL it all out. But I might do if I call this A, and I call this B, and I call this C, I might have to do all different. I might do them in that order. So part A says find the zeros. Well, one of the zeros is x equals 2. Another zero is x equals -1. Another zero, gross, is 3i. And another zero is -3i. And those are all your zeros. Part B, though, I say, what are the x-intercepts? Well, you can't graph this guy and this guy on a graph, right? It's imagine. It would have to be done on an imaginary axis, not on the regular xy one that we know. So the only x-intercepts that we have are actually 2, 0 and -1, 0. Those would be our x-intercepts. So part A, I would say here's 4 different zeros or roots or whatever you want to call them. And then part B, I would say here's your 2 x-intercepts. The other 2 you're not going to see. And then part 3 or part C is, oh yes, FOIL that out. Now my advice to you is when you FOIL these out, if you have these complex factors right here, make sure you FOIL them together, right? They'll always come in pairs, believe it or not, and that's coming up. They'll always come in pairs, so always FOIL them together. So when I'm FOILing this, I might just write it all out, but I'm definitely going to do those last 2 together. So there's a couple of ways you can FOIL. You know your ways. I would first FOIL, say, these first 2, and I would get x squared minus x minus 2. And then I would FOIL these guys right here. And what would that be? Now I'll be a little careful here. This will be x squared and then plus 3ix, and then minus 3ix, and then minus 9i squared. And you might be realizing why I said make sure you FOIL those together, because you'll see the 3ix's drop out because they cancel each other out. And remember, I squared is -1. So the way that's actually written now is x squared plus 9. And look at how pretty. All the imaginary numbers are gone, and we're feeling a whole lot better. In fact, I can still continue to FOIL this out. So some of you I know like that box method. I'm going to show you the box method in case you want it. It is just FOILing, but it's just kind of like a pretty FOIL. So notice I made a 2x3 box because I have a trinomial by a binomial. So I'm going to put the binomial here. I'm going to put the trinomial here. And then now you just find, in essence, the area of each box. So x squared times x squared is x to the 4th. And then I have 9x squared. And then I have -x cubed. And then I have what? -9x. And then I have minus 2x squareds. And then finally a -18. Or my final answer would be x to the 4th minus x cubed plus, now I have a x squared here and an x squared here. So is that 7x squareds minus a 9x minus an 18. And that is the polynomial that they would have given us and said factor, and we would have factored it into that. and then we would have turned those factors into zeros, and then we would have graphed it into that. So we've kind of gone full circle where now we have the zeros and we can make problems. So you can test your friends and you can make problems for them. Just write out a bunch of zeros, FOIL it out, and you can see if they can actually break it down. Now, this little green box here says that if you ever get a factor that is complex, if you ever get I didn't want to scribble it out, I wanted to highlight it. If you ever get an a plus bi as one of your factors, then its complex conjugate, a minus bi, has to be a factor also. There's no way around it. It's a rule. If one's a factor, the other's a factor. That's why up here I had both of them, because the fact is it's a rule. It has to happen, because they will FOIL out and they will make this fancy quadratic we have that you can't reduce. And that's what this other one says. This other one says that you will be able to do linear factors and irreducible quadratics. Irreducible quadratics are exactly that. Quadratics that can't be reduced, right? Because I can't do difference of squares because it's not a difference. And so you should be able to write everything down as linear factors and irreducible quadratic factors. So maybe I can jump into one more example here. Actually, I'm going to save that one for when we come back. So let me ask you a question, and we'll be back after this. Nice work. All right, now let's move on to this last example here. Suppose you have a polynomial with the zeros x equals 2 and x equals 1 plus I. Like, okay, interesting. What's the minimum degree? Well, you're like, well, there's 2 zeros there, so it must be x squared. Oh, but wait. They tried to trick us. Sure, x equals 2 is a great zero, and x equals 1 plus I just means it's imaginary. But wait, I automatically know, even though they didn't tell me that, 1 minus I must also be a zero. So now I know that we must have a minimum degree of 3. So this would have to be a third degree polynomial, or at least x cubed. All right, now that we've survived that little bit of thinking, we are going to move on to part B that says write the polynomial in factored form. Use linear factors. So here we go. If 2 is a factor, then x minus 2, if 2 is a 0, then x minus 2 is a factor. If 1 plus I is a 0, then x minus 1 plus I is a factor. If 1 minus I is a factor, well then x minus 1 minus I is also a factor. Now you can see those last two look a little gross. You could clean them up a little and call it x minus 2, x minus 1 minus I, and x minus 1 plus I. So you could do that if you wanted, and that would look probably a lot prettier. But there are linear factors. Notice linear factors x to the first power, and I do have x to the first power every time. Now they want us to write our polynomial as a function of linear and irreducible quadratics. So we got a linear suite, but this one's gross. So I want to get an irreducible quadratic for this guy, right? And they want real coefficients. They don't want imaginary numbers or complex numbers. So I could clean that up quite a bit. I would say, well, one factor is x minus 2. Everybody likes that. But this other one, I got to FOIL this out a little bit. So here again, I'll do my box. It's a trinomial with a trinomial. So I have x, negative 1, negative I. I have x, negative 1, positive I. And so what do I get? X squared minus x minus ix. Now I have minus x. I got plus 1. I got plus I. I got ix. I got negative I believe. And then I have negative I squared. And you might notice some things like I and negative I cancel. Ix and negative Ix cancel. And then I squared actually becomes negative 1. So this is really plus 1 right here. And so what would I be left with? Well, I would be left with, and I'm going to put it right here, x squared minus 2x, and then plus 1 and plus 1 is plus 2. And that is my irreducible quadratic. Notice the i's are all gone. And that's where I'd like to get it finally factored down to. And then this last step says, hey, all right, now can you write your polynomial function in standard form? In other words, can you multiply it all out and tell me what you have? Sure can. So I'm going to go ahead and multiply the x through. Now, instead of doing the box, I'll do it the old distribution way. You could still do the box, but if I bring the x through, I have x cubed minus 2x squared plus 2x. And then I'll distribute the negative 2 through. So negative 2x squared plus 4x minus 4. And my final answer for this thing is x cubed minus 4x squared plus 6x minus 4. And there is your beautiful foiled out problem. And that's what your polynomial would look like. All right, let me ask you a question, and I'll be right back after this short break. Nice job again. And I'm starting to get a tear because some of your effort has been really amazing. And I want you to keep it up. I want you to know you're awesome. Keep up the good work. But now let's finish this up. So as I look here at this final thing, this is like we're going to put it all together. And I give you a big, nasty fifth power problem, and you have to factor it. Oh, who's this crazy guy and what is he thinking? So just break down each little part when it comes to factoring. So first thing I'm going to do is I'm going to say, all right, well, to factor, it'd be really nice if I could do synthetic division. Okay. Well, synthetic division, what am I going to plug in my synthetic division? I don't know. How about that theorem, the rational root theorem that says all the factors of 9 over the factors of 3. Remember the last over the first. So factors of 9, not too bad, 1, 3, and 9. And the factors of 3 are 1 and 3. So it looks like I'm going to have to do like 1 and 1/3, 3 and 3/3. Oh, wait, that's just 1. 9 and 9/3, that's just 3. So there's really not that much, actually. There's just 1, 1/3, 3, and 9. Now remember, those are possible zeros. It doesn't mean they're going to work. It doesn't mean anything. It just means they're possible. So how do you do it? Now I'm going to even show you my synthetic division a little different. Not too different, but a little different. What I do is this. Coefficients across the top. 3, 1, negative 24, negative 8, negative 27, and negative 9. And then I'm going to try to test those numbers. So I'm going to start off with testing 1 because I'm hopeful that it works. So remember, you add straight down, and so you'll notice it's a little different. You multiply with what's in the box, so I multiply to the left, and then I add to the top. So 3 plus 1 is 4. 4 minus 24 is negative 20. Negative 20 minus 8 is negative 28. Negative 28 minus 27 is negative 55. Yuck. And now negative 55 and negative 9 is negative 64. And I cried a little bit. It didn't work. So maybe now I'll try 3. Maybe I should have tried 1/3. I'll try 3 and I'll go 9 plus 1 is 10. 30 minus 24 is 6. 18 minus 8 is 10. 30 minus 27 is 3. And 9 minus 9 is 0. Wow, nailed it. Got one. 3 works. That is fabulous. So I'm feeling pretty good. Really what you have now is, remember, this is your remainder. So this is your constant, your x squared, your x cubed, your x to the fourth. So you have a new problem all over. You're like 3x to the fourth plus 10x cubed plus 6x squared plus 10x plus 3. And again, you could do your factors of the last number over the factors of the first number. So things that you should try are, 1 and 3 over 1 and 3. So again, notice I didn't get to eliminate 3. It might be a factor again. It might not. I don't know, but it's still a possibility. So I will now jump onto this one and I will say 3, 10, 6, 10, 3. Now that 1/3 is bothering me, so I feel like I really want to try it, and I hope I don't regret it. But 3, 10, 6, 10, 3 looks good. I'm going to try 1/3. Okay, you ready? Add straight down, multiply, you get 1, and add it to the next one is 11. Who picked this? 11 over 3. Oh my gosh, really? 11 over 3 plus 6 over 3, that's 18 over 3. Not like 29 over 3. Okay, none of this is looking good. And this is just going to keep growing and growing and growing. So it's going to be something that does not get me a 0. And so I'm sad. But I'll move on. So maybe now I'll try -1. Haven't tried -1. So 3, -3 and 10 is 7. -7 and 6 is -1. 1 and 10 is 11. Boo, -11 and 3 is who knows what anymore because I'm sad. So -8. Let's try -3. Haven't done that. So 3 multiply -9 and 10 is 1. -3 and 6 is 3. -9 and 10 is 1. -3 and 3 is 0. Thank you. And so found it, found another factor or another 0. And the good news, we're left over with 3x. So this is, let's see, constant x squared, x cubed plus x squared plus 3x plus 1 equals 0. That's our new problem. You should try things like 1/3 and -1/3. 1/3 didn't work for me, so I'm probably going to think I should try -1/3. But here's the good news. I notice it factors by, it's 4 things, and it factors by grouping. Because notice here, I'll pull out an x squared, and I'll be left with 3x plus 1. Then you copy that sign down in the middle, and then you factor something out there. It can't, oh, okay, so 1, and I'm left with 3x plus 1. And then remember what factor by grouping says. This guy and this guy better be the same. And if they are, that's one factor. And then the outsides are the other factors. So, oh my gosh, life is good. I think I have just completed this problem, right? I have, from this guy right here, x minus 3 is a factor. From this guy, I have x plus 3 is a factor. From this guy, I have 3x plus 1 is a factor. And from here, I have x squared plus 1 is a factor. X squared plus 1 cannot be factored any farther. So there you have it. That is completely factored, and I feel pretty good. I just factored a very hard problem. I can tell you it has 3 x-intercepts, and it has 5 zeros total. And I think that was all I was asked to do. Finished, done, happy. Have a great day. See you tomorrow.